Okay, well, let's get started. I've got a definition for you, and then I want you to do some computations in a polynomial ring. So let me do this definition first. Okay, so this is the definition of the leading coefficient and the degree of a polynomial. So this should look familiar, things that you've seen before in maybe an algebra class. So we're going to let f of x be that polynomial in R adjoin x, and we need that an to be non-zero. Otherwise, what's the point? So we need that one to be non-zero. Then an is called the leading coefficient. So it's the coefficient for the highest power of x. Sorry, that's an x. And then the degree is the integer n, which is the highest power of x. Okay. All right. So here are some computations. So let's do this. Let me give you these functions first. So we'll say f of x equals, let's do 2x to the fourth, and let's say g of x equals 5x, and let's say h of x equals 1 plus 3x. So let's do compute. So we'll do example. And so for the first one, so we'll assume f, g, and h are in z adjoin x. And we're going to compute. Okay, so we're going to start by doing this. We're going to compute f times g and f times h. And while you're doing that, I just want you to pay attention to the degree of polynomials. Let's see if we can conjecture something about the degree. And then we're going to do the same computations with f, g, and h elements of z mod 6 adjoin x. When we want to compute I'll give you some time to compute those, and you can talk to your neighbors and see what you think is going on there. Okay, for you online people, I have these three functions, F, G, and H. Then I'm asking you to compute F times G and F times H. If we assume that the polynomial ring is Z adjoin X. And then we're going to do the same computations, but we're going to assume that the polynomial ring is Z mod 6 adjoin X. Okay, so we'll do F times G and F times H. So let me leave this here pointed at those functions so you can see them.
So it's gonna be like pi. So it just still be 10. I mean, would like we'd only be guaranteed that if x to the 5 is like 1, or like if x to the 5 we're looking for. Oh, so you just ignore the x.
Yeah, so the coefficients are in those rings.
So, okay, what would happen if we were to try to like use these polynomials as a function? Like if we tried to plug something in, they would start like, would they still be consistent in the modular arithmetic?
Well, so X could be something that's not in the ring of coefficients. I'm not sure if that answered your question or not.
Yeah, well, I was just thinking like if x were like pi or something, like you could do, like you do the mod 6 on the coefficient, but then you get but then when you plug in pi for x, you get two things that aren't congruent mod 6 being congruent to each other.
What do you mean?
Like, well, I don't know. Let me actually try it, I guess.
Okay. Okay, what did we get here? Did you have time to do FMG here? It's an X effect, yeah. Okay, and how about here?
Two x to the 4th plus 6x to the 6th.
All right, and did anyone notice anything about the degree of the product? Did you see what was happening with the degrees? Add the degrees. So when we did F, so we are seeing here that the degree of f of x plus the degree of g of x was equal to the degree of f of x, g of x. Right? And in the second one, we were seeing that the degree of f of x plus the degree of h of x is equal to the degree of f of x. And is that kind of consistent with your experience in algebra classes in the past? You've kind of seen this sort of thing. Okay. What happened when our coefficients were mod 6? What did this end up being? How about here? Just 2x. So what happened with degrees here? Yeah, so I think, did you say this was mod 6? Mod 6. Oh. Yeah.
Well, the second term is good. It was 6, so it went to 0, and then the first term is 6, so it's already mod 6.
Yeah, so how come that happened over there, but it didn't happen over here? What is it about that coefficient ring? There's 0 divisors there, right? So, and there are no 0 divisors in Z, right? So what we had here is that because we have 0 divisors, in Z16, the leading term could end up going away, right? Does that make sense? Okay. That leading term or that leading coefficient could end up being 0 if you have 0 divisors in your ring. Does that make sense? And so can we say a similar thing here with this? Could we make a similar statement here? Could we modify this statement to be true over there?
You take the modulus of degree of f times g. Oh, wait.
Well, that's an interesting idea. So you were thinking you take the
Well, I guess the degree is the exponent, so it didn't really do the same thing.
right. Do we need to do another example in Z mod 6 join X to see if we can? Let's do, we did F times G, we did F times H. Let's do G times H and see what does that give us? So we get 5x plus 15x cubed, which was 15, that's 3, 1, 6. Yeah. So sometimes it works the same and sometimes it doesn't, right?
I feel like you have to know what the coefficients are to know if it's going to disappear.
Mm-hmm. Yeah, we do. But we could modify this by doing what? We could change this equal sign to something else. Not congruent.
Less than or equal to?
I
Or
think
wait,
we would need greater
more
than,
than or equal to? Oh, yeah. plus,
greater
yeah.
than or equal to? Because here, degree of F plus degree of H is equal to, wait, 4 plus 2. Right, that's 6, right? And we got 4. So I think we need degree of, so I'll write that, degree of F plus degree of H is strictly greater than the degree of F times H, right? For that one. And then some of the other ones we got it equal to, right? And so what's happening is, why is that sum going to be greater? Well, because when I multiply that highest power might end up going away, right? So it's going to be, it can't be any bigger, right, than that, but it so it's going to be greater than or equal to. I wrote it backward. I should have written it the other way. That's the way it's written in the book, but anyway. Yeah, so that's the idea. So I'm gonna do theorem 4.2, theorem 4.2. And it's related to this. And we'll have 3 corollaries. And then I'm going to do the evaluations today, and then we'll be done. Sound good? So we're getting close to the end of what we're going to do here, because I was talking to Dr. Ortman, and I think we're just going to do 4.1 and then kind of stop. So what that means is that on Monday, we'll do the polynomial division algorithm, review for the test Wednesday, take the test Friday, and then the dead week, we'll just have time to review. So that'll be time. Bring in your old homeworks, and we'll just kind of spend time working through past problems and thinking about definitions and taking time to review. So it'll be kind of a chill week. So you will have, I think there'll be one homework that's due that week on 4-1, but. Okay, so theorem 4.2. Okay, so if R is, what does R need to be to make that equality hold? Needs to be an integral domain, right? Needs to be an integral domain, because if it has 0 divisors, then this is not going to work out. So if R is an integral domain, and f of x, g of x are non-zero polynomials in R of x. Which I'm not really sure why the non-zero polynomial needs to be there, because the degrees should work out the same. Although is this not, because if they're, yeah, it's like you can't ever make the degree, if the degree is 0, then the equality is still going to hold. So I'm not really sure why the non-zero part, maybe it's in the proof somewhere that we need the non-zero. Anyway, in our adjoint x, then the degree of alpha x dx equals x. Oh, I was going to tell you all, I had so much fun grading homework 19 because y'all came up with some really interesting examples and counterexamples on there. So that was actually really fun seeing the different things you all came up with. So I just want to tell you all that. So I just graded that yesterday and I had a good time. Okay, so here's the proof. I don't always enjoy grading, you know. I mean, that may come as a surprise, but but that was fun. Okay, so that's what we want to prove. All right, well, how are we going to prove it? What do we need to do? Well, I mean, the proofs in this section are really going to be a whole lot of multiplying polynomials that look like this, right? And keeping track of all the coefficients and all the, all that stuff. So yeah, Colin?
Well, we're gonna be doing it for, I guess, it doesn't specify the degree we want, so we want like an nth degree, so would it be better to do like a fraction?
I don't know that we'll need it, actually. Yeah, so what we really need, F will have a degree and G will have a degree, right? So we'll have an N and an M floating around, okay? So that's what we'll end up with. So let's just let F and G be non-zero polynomials in there, and then they'll each have some sort of degree. So we'll just call them those things. So we'll use f of x, we'll use the a's with the subscripts for its coefficients and go up to n. And for g of x, we'll use b's for the subscripts and go up to m. So we have 2 different polynomials there. And then I could say, so the degree of f of x equals n, and the degree of g of x. Right, so that's the way we've defined those functions. So then what is f times g? So if I do f of x times g of x, well, what do I get? Well, when I multiply those together, what's my constant term going to be? A naught b naught. Yeah, so the constant term is a naught b naught. Okay, what's going to be the terms that have x the first in them? Well, I'll get an x to the first one, I multiply that by that. Right? And I'll get an x to the first one, I multiply that by that. Right? So I'll have a naught b1 x, so I'll have a naught b1 plus a1 b naught. And then at some point, we're gonna have to do a dot, dot, dot here, because we're not gonna be able to write them all out. But if you want to play around with this, you could kind of start to try to see what the pattern, let's do a few more just so that we can kind of see the pattern here. I don't know, have you all done this kind of thing before, multiply these together and really thought about what they need to be? Maybe I should have put my a2 x squared anyway. So for my x squared terms, I'll get them when I multiply this x squared term by that constant, right? And I'll get them when I multiply this x term by that x term. And I'll get an x squared if I multiply this constant by that x squared term, right? So those are the three ways that I can get squared terms. So I'll have a naught b2 plus a1 b1 plus a2 b naught x squared. And you'll see some really nice patterns emerging here. You see that? What's the x cubed one going to be? So how do I get a cubic term? Well, if I multiply the constant here by the cubic term there, I'll get a cubic, right? Or if I multiply the linear term here by the quadratic term there, or the quadratic term here by the linear one here, or the cubic one here by the constant one there, right? That's the way I'll get cubic. So I'll have a naught b cubed plus a1 b squared plus a2 b1 plus a3. What are you noticing about the pattern here? They do get bigger. Yes, they do get bigger. Are you noticing indices? Those indices sum to. So here the indices all sum to 3, right? And here the indices all sum to 2, and so on. So you'll start to see that. Okay, I just wanted to do a few of those so that you kind of see where this is leading. They get big and then they get smaller, right? So as we get to the end, how can we get the highest term? Well, the only way we can get the biggest term, the biggest degree term is by multiplying the biggest degree term here by the biggest degree term there, right? So that's the only way I can get that. So the biggest one I'll have is a(n) bm times x to the n plus m. And that'll be the biggest one. What about the next biggest one? Well, I can get that one by doing a(n minus 1) bm plus a(n bm minus 1 x to the n plus m minus 1, right? So that'll be the next one down. So it only has 2 coefficients summed up there. Anyway, so yeah, so those kinds of patterns. Is anyone taking advanced linear algebra maybe in the spring? So when you do proofs in advanced linear algebra, you have to really keep track of all the indices and how you're multiplying things. And so you have a lot of proofs that look like this, where you've got a lot of things. Yeah, is that called telescopic? So no, like a telescoping would be when like if you had some beginning term and some ending term and all the middle terms canceled out, like added to 0, then it would be telescoping because it kind of collapses in on itself. Yeah. So you see the telescoping, probably the place you've seen it is when you did the proof of the sum of a geometric series. Do you remember doing that? Proving the sum of a geometric series? It's kind of a classic proof. So if you haven't done it in a while, you can go look at. Some of you did it actually. When we were doing the induction proofs, and then some of you did it directly using that telescoping bit. And I was like, oh man, I wanted you to do induction. But anyway, so you probably just found it in a calculus textbook or something. But yes.
I've seen I've seen a proof of the geometric series formula, but it wasn't telescoping, and now that I think about it, I wonder if it wasn't technically a correct proof, but it used like bootstrapping where the geometric series contains like it contains like a multiple of itself, and you can back substitute.
Yes, and so it's similar to that, because, well, anyway, we can talk about this another time. Okay, so there's my, so anyway, so when I multiplied them all out, sorry, you online people, you can't see all this mess yet that I've got. Okay, how do I, whoop. So I got all of this and we were multiplying it all out. And then when we got to the last term, we saw we had a n bm times x to the n plus m. And so we can say that the degree, and how do we know, okay, so here's the thing. How do we know that that's the biggest term? Or how do we know that that term doesn't go to 0? Right, remember that was the thing we had when we were in Z mod 6 adjoint x? That when we multiplied an times bm, we ended up getting something that was 0, right? So why is that not going to happen here? What are you going to say? Yes, so I know it's non-zero polynomial, so I can actually make this so that let's say this. I need to say this where an bm are non-zero. I probably needed to say that to get the degree bit, right? And then Zach. R is an integral domain, right? R is an integral domain. So I know that a and bm is non-zero since R is an integral domain. So I know that an and bm are non-zero elements, and if this is an integral domain, you can't multiply non-zero elements and get 0. Okay, so the degree, I'm out of space. So the degree of the sum of the degree of f of x and the degree of g of x is equal to this. Or let's do it this way: the degree of f of x g of x is equal to the degree of f of x plus the degree of g of x. So I got down to the end right there. Ooh. All right, so then let's do some corollaries of that. So corollary 4.3. So since it's a corollary, I'm going to leave the proof up there. Yeah, Colin?
So did they say, you mentioned that non-zero part, did they say that because
this part,
if one of them was a zero polynomial and the other one had x terms, would it still?
oh yeah, maybe that's it.
Oh.
Yeah, maybe that's it. I was thinking of them both being 0, but I think you're right. They have to be non-zero because if one of them were 0 and one of them had x's, it would figure it all out. Yeah. Okay. Thank you. That helped me make. Well, anytime you're reading a theorem and you see these conditions, you should always go, why is that condition there? You know, what's going to break down if that condition weren't there? Because you know, in the textbook, they're not going to put a condition in there that's not needed. All right, so here's corollary 4.3. It says if R is an integral domain, so is R adjoint X. Let's prove that. Well, actually, it's a corollary, right? So the proof actually it comes up here. I proved that the product of non-zero polynomials is a non-zero polynomial by this proof, right? So we just in the proof of theorem 4.2, we showed that the product of non-zero polynomials And why is it a non-zero polynomial? Because that first leading term is non-zero, right? If it, to be a zero polynomial, you have to have every term be zero, every coefficient be zero. So you show that it gives you a non-zero polynomial. Okay, what about the next corollary? Corollary 3.4, or sorry, 4.4. What am I doing here? Let me count. This is let R be a ring. This is any ring, not necessarily an integral domain. We're going to have a similar thing. The degree of f of x g of x is less than or equal to the degree of x. Why is that the case? Well, it's going to be the case because if we have zero divisors, you know, you could have that leading term end up being zero, which would seem to make sense. The book doesn't even have a proof at all for this corollary. So I think we've seen this. This is true. Okay, I got one more corollary. We'll prove this one. And then we'll be done for today. Oh, whoops. Totally didn't forgot to move it over for those two okay, corollary 4.3 and 4.4 were just from the textbook, so y'all can figure that out. Okay, here's corollary 4.5. Well, the one thing about my videos being so terrible is that it incentivizes you to actually come to class. I want to watch this video. Oh my gosh. Okay. So, all right. So here's let R be an integral domain and f of x a polynomial and R join x. Okay. F of x is a unit in R of x. We haven't talked about units in a bit. We talked about them last time. Do you have a feeling for when it will be a unit in R join x? Well, I'll write it down and then I think you'll go, oh yeah. So it's if and only if f of x is a constant polynomial that is a unit in R. So if you remember in Z adjoin X, we were talking about that the units are plus or minus 1, right? The units were plus or minus 1 in Z adjoin X. We kind of talked about that on Wednesday, just by example, but that's going to be true in general. So the only way to get units in these polynomial rings is if they're constant polynomials and that constant is a unit in the ring. In particular, if f is a field, the units in f of x, f adjoin x, are the non-zero constants in f. So I'll do a couple of examples. And C adjoin X. Units are plus or minus 1. And Q adjoin X. So the rationals are a field, right? Because they have multiplicative inverses for every element. You can flip things over in Q. So the units are basically it's all of Q except 0. So Q set minus 0. We haven't used this in a little bit. Well, I think the book sometimes is using actually a minus sign for set minus. I've grown up with using that one for set minus, so it's a little hard to break. But this is the rationals. We're going to leave out 0. Okay, so that's the idea there. Okay, so let's prove this real quick, and then we'll be done for today. Move my thing over here. So for the proof, yeah, it is an if and only if statement, right? So we're gonna have to go both ways. So we're gonna go this way first. So we're gonna assume that f of x is a unit and R adjoin x. Then, what does it mean to be a unit? There exists some g of x such that f of x, g of x equals 1 or. Yeah, Colin?
On that in particular thing, do we,
We're not gonna prove that part. Like,
Oh.
that's just a comment.
oh, okay, I was just gonna ask real quick, is there a general version of the idea of a constant in a field, or is that talking about just like real numbers or something? Like
Oh,
non-zero constants?
I meant this. No. The non-zero, let's say elements.
Oh.
Maybe that makes more sense. There you go. Yeah. Yeah, I kind of went rogue there because it says, well, actually, no, in the book, look here. It says the non-zero constants in F, which is funny. So I think what the book said that, which I think the book should have said that differently. Because I think you're right. I think I like the non-zero elements of it. So maybe we could say, so let's do this way. Let's do this. The units of f of x are the constant polynomials that are non-zero elements of f. How about that? Feel better? So they're constant. So in f adjoin x, they're constant polynomials.
Okay,
right.
we definitely know what a constant polynomial is.
Yes.
So, okay,
A constant polynomial has,
degrees, okay, or degree.
degree
Yeah,
0.
zero.
Degree 0. And it's the constant polynomials that are non-zero elements of f. So everything except the 0 polynomial.
Okay,
That's a constant.
That's-
polynomial. Is that better?
yeah, I like that, that's good.
Okay. Right. So I've got this thing here. Well, what am I going to use? Well, what's the only thing I have that we've done today? This bit about degrees, right? So I have that this f times g. So by theorem 4.2, the degree, wait, do I know that? Oh, I know it's an integral domain, okay, right? So I can use theorem 4.2 directly, right? Okay, so I can use theorem 4.2. And so the degree of f of x g of x is equal to the degree of f of x plus degree of g of x. Well, what does that tell me? So, well, what's the degree of 1R? What's the degree of that? It doesn't have any x's on there, right? So it's a 0 degree polynomial, right? So that means that the degree of f of x equals 0 and the degree of g of x equals 0. Right? We can't have a negative degree. The degree has to be a positive integer. Okay. So since degrees of polynomials are non-negative, we have that the degree of f is and degree of g is 0. Therefore, f and g are constant polynomials, that is constant in the ring. I'm just going to call it R, and g of x equal s for R, S in our ring R. Right? They're constant polynomials, so they're just equal to some elements of the ring R. And so then we have, well, if f of x is R and g of x is S, I can replace them here, right? So R times S equals 1R. And what does that mean about R? What does that mean about this R? It is a what? The unit in the ring R. Well, and what was R? R was f of x. So f of x is a unit. So f of x is a constant polynomial. Well, so let's say it this way. F of x is a constant polynomial. So how about I say it that way, because then that matches the theorem. Okay, so that's one direction, and the other direction is going to be like 2 lines, because what? If I assume that f of x is a constant polynomial that's a unit in R, right? Then, well, it's going to be a unit in R join x, right? So assume that f of x equals R for R, a unit in R, actually in R. Then there exists some S in R such that R times S equals 1R. But, so for g of x equal to that S right there, we have f of x times g of x equals RS equals 1R. So F is a unit in a R join X. So I did that kind of fast. Was that clear enough? Yeah. So it's funny because we have these elements of the ring R, and then we have to think of them as elements of R join X. We have to think of them as constant polynomials, not just elements of R, right? So it's just kind of, you have to kind of shift your way of thinking about those elements. Okay, that's all I've got. Oh crap, we only have 7 minutes. Ugh, I meant to give you more time on this. Let's just stop that, and I can try for Monday because I want you to have more time. These are really long. It's like 2 pages front and back. You think, I don't know. You think 7 minutes is enough time?
Monday.
Huh?
I said Monday.
Monday. Okay, we'll try Monday. Okay, y'all go home. Oh, some of you had questions on the homework. So if you had questions, you can talk to me.